Hello to everyone from around the world, and welcome to today's webinar, which is part 2 of the Overcome High-Speed Digital Design Challenges series titled Modeling Optical Fiber Communication with Channel Simulation, brought to you by Agilent Technologies and DesignCon community. We have just a few short announcements before we begin. This webinar is designed to be interactive, so please ask questions at any time during the presentation by typing in the text area and clicking the Submit button. Our presenter will answer your questions at the end of the webinar, but please enter them whenever they come to mind. Later in the program, we will ask you to complete a short survey. Please take a moment to fill this out. Your feedback is important to us and will provide Agilent and DesignCon community with valuable information on the subjects covered in this webinar and how we can improve future broadcasts. The survey will open for you at the beginning of the Q&A session. Additionally, you can launch the feedback form by using the survey button. And now on to the presentation. It's my pleasure to introduce our presenter, Graham Riley, Senior Application Engineer at Agilent ESOF EDA, and joining us during the Q&A will be Colin Warwick, Product Manager with Agilent ESOF EDA. Welcome, Graham and Colin. I'll now hand it over to Graham to begin the presentation.
Thank you, Jessica. So welcome, everyone, and thank you for attending this second webcast in the Overcome High-Speed Digital Design Challenges series. The topic for today's webcast is modeling optical fiber communication with channel simulation. In this presentation, we'll be looking at the challenge of designing physical layer of a communication channel, which includes an optical fiber link. We'll discuss the options for simulation of such a channel, and we'll describe how channel simulation is well suited to that task. So here's the agenda for the presentation. You'll see that we will look at some of the market drivers, the need for speed and capacity in optical links. We'll then look at some of the choices for simulating a channel. We'll move on, and then we'll look at channel simulation as a specific topic, and particularly at the modeling that's required for that kind of simulation and the simulation technique itself. Then we'll move on and we'll look at a specific case of using channel simulation and including an optical link. Before we get into the technical discussion, let's quickly consider some of the market drivers for the kind of optical-based channel we're talking about today. So here in the first slide, you'll see the truly amazing number of 10 to the 21 as zettabyte. This is something that's coming up to the internet as a traffic threshold, and I thought that was a truly remarkable figure, and it really represents the primary driver that we're all aware of for things to get faster. Why is this thing growing so quickly? Well, it's really you and me. We're using more and more digital media. Interesting, though, is to think, well, where's all this media sourced? Where is all this data served to us, and what are the implications there? So data centers like the one you see here are springing up all over the country and all over the world. And these are centers which serve this tremendous amount of bandwidth. And the kind of link we're talking about today now really forms the backbone of such data centers. And you'll see in the graphic on the bottom left corner that data rates are increasing at an almost exponential rate here. We're looking at 40 gigabit Ethernet, 100 gigabit Ethernet, and perhaps even beyond that coming up soon. So what did we do to address this? What is the industry doing to address this? Well, we're looking at many different techniques for the physical layer itself, and you can see here just a few of them, a few of the options listed, anything from modulation schemes, increasing the lane signaling rate, using multiplexing with multiple wires, multiple fibers, and even now considering wave division multiplexing in optical fibers. On top of those techniques, there are also technologies to consider. Each of these standards has its own drivers, but you have to implement, and that means choosing a semiconductor process, choosing packaging, choosing connectors, and those kinds of things. If you look at this from a system level and look at the Ethernet view, if you like, of this issue, you can see here that in the physical layer, we have a very tight mixture of electrical functions and optical functions and media, all of which need to be looked at together in order to make good choices with respect to future implementations and even implementations of current standards. So having to make choices really starts to talk to the world of simulation. So let's go and ask the question to ourselves: how do I quantify, how do I qualify my physical layer design activity? So yeah, there are a lot of trade-offs to be made at all different levels, and you probably recognize yourself here in one of those green arrows, or the yellow arrow, or the red arrow. You're probably working in one of those areas right now, and you're having to make these trade-offs. That really does drive you towards simulation to explore the design space, whether you're designing a component or a module or a whole system. If you look specifically at the physical layer itself as a simulation channel, there are some general attributes that come to mind. First of all, you need accurate models, and you'll need good simulators for these links. Whether it's the component, a link as a whole, you need accuracy for that. And then ideally, you want to go beyond just being able to simulate. You need to be able to link your simulation to a complete design, that is, the whole thing end to end, and be able to validate with your measurement equipment and your measurement flows. So those are some of the general attributes of this simulation environment that you would need. If we move specifically, we'll take a case here of an optical transceiver. You can see here that this is an electrical to electrical kind of link. It really does have an electrical channel, which is probably modeled with some distributed model like S parameters, for example. There's DSP functionality, clock and data recovery, equalization, those kinds of things. There's clearly the optical part of the link itself, and there are going to be some circuit models involved, so many different models. And on top of that, we have specifications to meet. Clearly there'll be jitter, probably I, but one of the key specifications at the system level is the error rate, and those tend to be less than or equal to 10 to the minus 15, and that itself is a challenge because that requires a large number of bits to be simulated. So we'll look at that in detail in a moment. So that kind of gives you a framework, if you like, for thinking about the things that you need to simulate in this kind of electrical optical kind of channel. So let's look at some specific options that you might consider, you may even be using right now. First of all, there is what I call SPICE, circuit simulation. You'll see here on the slide that there are some good things about using this kind of circuit level approach, and there are some difficulties. First of all, you can use circuit level models. That's good because a lot of the early design work, the component level design, has those models available to you. You have many different forms of simulation: DC for bias point, AC, time domain. You can look at waveforms at any arbitrary node. You can include technology. You can include EM models for channel and packaging and those kinds of things, and you can include S parameters wherever they come from. And the good thing is most everybody out there speaks SPICE. We all know what that does. We know how to set it up. We know how to run it. On the disadvantages side, SPICE really has no practical way of implementing DSP functions. It can also be slow, and the more complicated your system is, clearly the slower it gets. I've quoted 10 to the 6 bits per day here. It can be that. It's about that for the schematic you see behind this graphic. But it could even be less than that if you have a more complicated system. Because of that, it has pretty limited bit error rate capability, and one of the other challenges is there's really no native optical support, no concept of optical signaling. Yeah, you can do it by using special case or using some kind of electrical analog, but that's extra work. And you will have this issue with proprietary model encryption that comes along if you're trying to protect IP. So another class of simulator would be what I would generically call the system simulator here. This is generally a high-level engine, uses behavioral models, you can see here that, yes, well, the good thing here is, yes, absolutely, we can do DSP modeling and implement DSP functions. We can do system-level measurements typically in conjunction perhaps with measurement-related software. As you see here on this particular graphic, that's the Agilent DCA software. It can be fast for some things. Using compiled models, you can really get some good speed. It can be used to generate C++. Now, that's important, and we'll talk about that a little later when we talk about modeling in the context of channel simulation. It takes language-based models, HDL models, C models, math language models. It also can deal with electrical and optical together because, in essence, most of these simulators are really not passing voltages and currents. They're really working with numbers. So that's something that can be built into the models. Very flexible. On the downside, very few circuit models. It's hard to include packaging and channel in this at a high fidelity level. It's also difficult to include any technology related to those things. Limited BER capability. That's really down to the fact that it can be fast, but is it fast enough? Slow is a relative term as I've used it here. Again, the more functionality you include, the slower it will become. Another thing to be aware of, there are many different kinds of system simulation, and that results in non-standard models, non-transportable models. And one last thing for those of us who are circuit-minded, very often the setup and the terminology is...
The stream you have requested is currently unavailable. Please check the event listing, as the event has either not started or is currently being prepared for on-demand viewing and will be available shortly.
Let's consider a third class, the one we're going to focus on here as an option for working with channels. So channel simulation, as the name implies, this was designed and it was implemented specifically to look at a communications channel. As such, you can see that it has some very important pros here. We can look at waveforms, we can look at bit error rate, we can look at bathtubs, we can look at jitter, all of the kinds of metrics that you'd be associating with a communications channel. It has DSP capability, which is good. It's fast to extremely fast, and that becomes important when you're looking at things like bit error rate. And you can include EM models, parameter models, linear circuit models directly into the channel. And as such, and the good news here is that one of those trade-offs that we talked about earlier, which is how does my DSP function interact with my channel, you can actually do that very, very easily in this particular kind of simulation. On the downside, well, yes, there's certainly the need here for specialized models of the transmitters and receivers, and they're called IBIS AMI models, and we'll talk about that in a moment. And for some of us, or in terms of if you're a circuit designer, you may not be familiar with some of the DSP concepts. But again, it's not an open DSP. The DSP is really put into the simulation by a modeler, somebody who's produced the transmit receive models, and you'll see that later on. And one other thing is this is an evolving standard, and it's evolving in a positive direction, which is the good news. So you will have to sort of keep up with the changes, and I'll discuss some of the things that we're looking at there in terms of the future. So let's dive a little bit deeper into using channel simulation, and this really does break down into two parts. Given that channel simulation is a very good option for EOE type phi, let's break it down into two components so we can kind of get a handle on it. The first is those IBIS AMI models that are used to model transmit and receive, and also mid-channel functions, which we'll come to in a bit. And then we can also look at channel simulation as a technique, and we'll do that in the coming slides. So IBIS AMI, this stands for, well, IBIS, a lot of you are familiar with that. It's the input-output buffer standard. AMI stands for Algorithmic Modeling Interface, and this is an extension to IBIS, included in IBIS version 5, that allows us to add to that initial IBIS functionality algorithmic functions. So this is the DSP part, the equalizers, the clock and data recovery, those kinds of things. And it's truly an extension to IBIS in the sense that an IBIS file is the key file, and then the algorithmic section is added to that file, and then we add some extra information to the model in order to deal with that. So here, this is just a little little background on IBIS 5.0, you'll see the link there to the industry body. IBIS 5.0, which started the AMI part, goes back as far as 2008, and the industry has been looking at this and slowly adopting since that time. 5.1, which was this year, was really as a result of a lot of feedback from the early standard. And 5.2, due sometime this year, maybe next year. In my note there, it is a committee. This is what happens. That will include some new and major enhancements to the AMI flow, improvements to jitter. And one specific thing I want to bring out here is mid-channel repeaters targeted for this release as well. And if you want to look up the specification or the information on that, if you look up BIRD 156, that's the particular one that relates to mid-channel. And this is how, as you'll see later, we'll put optical links into the context of channel simulation. So what does the traditional flow and the IBIS AMI flow look like? Well, traditional flow takes place in a SPICE simulator. It has the IBIS buffer models and a traditional text-based IBIS file. Now, the IBIS AMI flow does require you to use the channel simulation. So IBIS AMI models don't work in a SPICE engine. They really are designed to work within the context of a specialized engine. And again, it starts with the IBIS text file, but there are two extra files that allow us to go ahead and put the signal processing functionality for the channel into the channel simulation. So what are the benefits of the IBIS AMI flow other than the capability that we've talked about? Well, one clear benefit is portability and IP protection. As you'll see, that the core of the model is a compiled C model, which means it's basically I'll say encrypted. It's not encrypted, of course, but a compiled model gives you a good level of security. And the nice thing is, because it's defined by a standard, it's also portable. It means you can take it to different simulators and share it between yourself and your customer, or get it from your vendor. So that comes to the interoperability. Nice thing there is that you could take a transmitter from vendor A and a receiver from vendor B, and if you're using IBIS AMI standard models, you should be able to work with them together. One of the other benefits, because we're working at channel simulation, we can get to really low BER contours, and we'll talk about specifically how that's done in a while. And the last one really is flexibility. And one of the things to really get to here is, yes, you can do sweeping of model-specific parameters and channel parameters, and that allows you to really interact with that choice between DSP function and channel to understand your DSP, your emphasis, your EQ, look at CDR functionality in the context of a real high-fidelity analog channel model. So what is the flow for IBIS AMI? So we'll cover this a bit more in detail with the channel simulation itself, but here is what it looks like. When you consider a system with a transmitter at one side and a receiver at the other, and a channel in the middle, the IBIS AMI models really they come into two parts. There is the IBIS section and the algorithmic section. And what the simulator will do with this information is it will build a composite channel from the IBIS sections and your channel information, and that is something that will be characterized using an impulse response. And then the transmit and receive DSP functionality are treated separately. And that's this ability to take that center section and do an impulse response, characterize it as an LTI, a linear time invariant section. That is what gives us the access to speed that we're going to talk about. Interestingly, there is a barrier, if you like, a high impedance barrier between the algorithmic function and the IBIS function, so they don't talk to each other. So there is a functional split there, but that really just is representing or formalizing what exists in the real circuit in most cases, in any case. One other thing, as IBIS AMI is currently written in the standard, this is a differential model. Okay, so that's something else to be aware of. Good thing is this does support simulations orders of magnitude faster than SPICE. So here are the three file types. I'll just go into a little detail here. Three file types for IBIS AMI. There's the .ibis file, which is the ASCII text file. There is a new ASCII text file called the .ami file, and that specifies the model parameters, and that's what's used by the simulator to access the model. And there is also the executable, which contains the algorithmic behavior per the AMI standard. These three file types will be transported as a group that constitutes the model. So if someone talks about an IBIS AMI model, it is really three files. If you look in the IBIS file, well, most of you, I imagine, will be familiar with that particular kind of file. Here is an example of the extra section that needs to be included, the algorithmic model section. And you'll see here that it basically specifies three things: the platform compiler, with the number of bits for the particular platform, the DLL file name, and the name of the AMI file. Those are the things that the IBIS file uses to clue the simulator in, if you like, that there's an AMI section associated with the model. So the AMI file looks like this. It's really not something that you, as if you were a consumer of a model, you would be given this file, but it's not something you would typically interact with. You would not edit this. This is something that the model developer will typically provide you. But it's useful to know what's in here. There are reserved parameters that are defined by the standard, and then there are model-specific parameters, things that the model generator has decided to give you access to, or rather give the simulator access to, so that you can interact with them. And then the executable file itself, that has the algorithmic information in it. It's a binary file, so there's the protection that you have. Notice that it's compiled for a specific platform. So if you're using Windows 32, you'll need one DLL. If you're using Windows 64-bit, you'll need a different DLL. If you're using Linux 64-bit, you'll need a different DLL. You can provide all of these files together, and the simulator will choose the correct one for the host platform. And the good news is, again, because this is standard, these models from different vendors are supposed to work with each other. Looking at what those files represent from a diagram perspective, so get a handle on where they fit in. So if you look at the diagram here, you'll see on the left side there are three transmitters. One is the primary transmitter, and there are two aggressor transmitters. And then on the far side there is the receiver, and in the middle there's the channel. You can see that there are algorithmic models associated with the AMI files and the DLL files. The IBIS files are lumped into the composite channel along with whatever the channel description is that you have. So that's what the files represent from a systems perspective. So we've talked about IBIS AMI files. Of course, the good question is, is it hard to create these files? Well, AMI is a behavioral representation of a complex analog digital DSP type function, and it is in compiled C code. So there's the target, if you like. Most people who are circuit designers or signal integrity guys are not proficient in C programs. Sorry if any of you out there are. I'm probably talking to myself at this point, but that's not something that's typically in our core skill set. So ideally, what we need is an automated tool to generate these IBIS AMI models for our customers. If you're in the business of generating a model, it would be really good to have such a tool. There is a tool that will do this for you on the market. It's SystemVue. Just a couple of words about SystemVue here. It is a system-level platform, as we discussed earlier, that uses many different kinds of modeling, including C++ type models. It's very fast and a very flexible environment. It has inside of it a library of common functions models, if you like. You see them there: FIR, IIR, DFE, CDR. They're S parameters. these are things that, if you like, are the seed of any modeling exercise to generate an IBIS AMI model. They can be customized. You can write your own models. Inside of that library, we already have 130 models, which, if you include them in a system, will allow you to generate C code. So that's a good thing, because that is, if you like, the core of generating an AMI model. And we've formalized that with a user interface in SystemVue for AMI model generation. And it's essentially a very, once you have the working and validated system model, you're able to generate the AMI function from that very, very easily through an interface. And last but not least, when you're developing a model, you need to be able to validate it. So that particular interface also talks to our DCA scope software, and it allows you to compare exact simulated waveforms versus measured waveforms. So again, very tight in terms of validating your model. Specifically for optical links, we provided 5 models inside of there in the library that you can use, parameterized behavioral models for 5 key elements that are used in an optical link. Our targeting for these first 5 models was really what we call rack-to-rack, so it's a multi-mode fiber-type environment. So there's a VCSEL driver, a VCSEL model, the multi-mode fiber itself, a pin model, and a transimpedance amplifier. So those are the 5 models that we've included specifically to support an optical link as part of the channel. So that's IBIS AMI modeling, what it is, what it does, and how you might generate such a model. So let's look at the simulation technique itself. So channel simulation is really a new class of simulator. I say new, it's been around for quite some time now. It's really dedicated, as I said earlier, to just working with channels, electrical channels, and now with extension optical links as well. The composite channel, that's anything between the algorithmic transmitter and receiver, is characterized as linear time invariant, and that gives us access to convolutional superposition techniques and statistical methods to get at these results really quickly. So let's look here at this particular slide. This gives you some insight into some how we access that speed and some of the trade-offs. On the left column, we're talking here netlist IBIS traditional flow. That's SPICE. So it's computationally expensive. We talked about that, but very general purpose. So you've got really no restrictions about the kind of model you can put in there in terms of in terms of whether it's nonlinear or linear, those kinds of things. IBIS AMI breaks down into 2. So channel simulation has 2 modes. One is superposition of bits. This is a time domain technique. It allows you to be very flexible in terms of the transmitter and receiver, but places the constraint on the channel that it's linear time invariant. And that's actually a reasonable constraint when you think about the kinds of channels that you're working with, on the electrical side anyway. Let's focus that on electrical. And then there is an addition to that technique, which gives you access through statistical methods to very, very high bit error rate low, I should say. 10 to the minus 18 or lower. And you can see that as comparison to SPICE 10 to the minus 3 and bit by bit 10 to the minus 6 within 1 minute. The constraint with statistical mode is simply this, that yes, the channel needs to be linear time invariant, but so do the transmit and receive. Transmitters, that's usually okay on the receive side. If you had some kind of nonlinear functionality like a DFE, then you would need to think about that very carefully, decide whether or not you could have a linearized model of that and still get useful information. And in many cases, you can. So that is the trade-off, if you like, from getting from the fully general purpose but slow SPICE environment to the extremely fast statistical environment that's available inside the channel thing. Again, this is just a diagram here that kind of shows you how this all bolts together. So on the left side, you'll see a transmitter algorithmic section. There's a pseudo-random bit sequence in there that can include, some kind of encoding. We then we can add in jitter to that. You can then apply equalization. So that's, if you like, all of the transmit DSP, so that the EQ is probably some kind of feed-forward equalizer, emphasis, that kind of thing. Then there is the channel itself, and you can see I've generalized it into analog components, maybe a distributed model or more analog components. The IBIS part of the AMI model is part of that picture. But you could also include resistors and capacitors and transmission line models and those kinds of things in this particular section. And then when we get to the receive side, you'll see that the waveform, which is basically the combination between the transmitter and the channel, that is applied to the receiver at the input. Then we can deal with receiver timing jitter, equalization, clock and data recovery. And then the output becomes what is then your received signal and clock ticks as well if you need them. Does it work? Is it that's a good, reasonable question to ask. How does this look when you actually use it? Well, this was a test that we did a little while ago with a Tyco backplane. We took the S-parameter model and put it into the system simulator the channel simulator, and compared, what you measured with the scope with what came out of the simulator, and the results were an extremely good agreement. What differences there were really explained by the fact that there were some imperfections in the measurement that we did not include in the simulation, but the difference in result was very small, and the agreement extremely good. So it's there's a proof of that it's a really good technique in terms of accuracy. What kind of results can you get at? Well, here are some typical before and after type answers. It's not a particularly large change here. If you look at the slide closely, you'll see that the after receiver eye width is a little narrower because we've included some receiver jitter in the eye. And you'll see bathtub there, you'll see summary, and you could also include things like jitter and those kinds of things. So that's the kind of information you can get out of a channel simulator. We'll dive in just quickly into some details here. I think it's worth kind of looking at how this channel simulator works with this environment in just a little more depth. So you can see here on the set one, the very first thing that is done is that you calculate the impulse response for the channel. Now again, when we talk about channel, we're talking about the composite channel. That's all of the stuff that's going to be LTI, including the IBIS at the output of the TX and the IBIS at the input of the receiver. So those things are combined. And then effectively, there are two modes once you have that impulse response. One is a bit-by-bit time domain, if you like, which is a superposition of bits, as you see there. And then there's also statistical techniques, which takes the impulse and the signal distributions and produces an answer in that way. So looking at step one, the characterization, here is like a blow-by-blow account of how that works. The top is, here's your channel. The second diagram is really saying, well, the impulse response, we take a step response of everything up to the between the transmitter and receiver, including the channel, and that gives us that information, and then we calculate the impulse response from the step response. So that is the characterization of the channel that goes on in the background. So you don't see these schematics. That's something the simulator deals with for you. Then there is another part of evaluating an AMI model, which is kind of detailed, but I'll bring it up here because it's important to kind of understand that this is part of the picture. Because you can have an LTI or a nonlinear versions of the model, there's something called AMI init. And AMI init is essentially a flag, if you like, that says, can this model modify an impulse response? And for statistical simulation, this has to be true for it to be valid. So what this allows a model to do is to take an input response and modify it and produce a modified impulse response. So if you look at the flow at the top, this is kind of a little different because what you do is you take the channel impulse response and through AMI init, modify it to give you a modified impulse, and then that is what is fed to the receiver. And this is the statistical methodology. And then step 2, what goes on from here? So if it's bit by bit, the model will typically have something called a getWave function, and that allows the model to work with waveforms. Again, I'm not going to go into a lot of detail here, but just to set the thought in your mind that there is some work that the modeler has to do to specify these behaviors inside of the model. And that allows you to do bit by bit, and that allows you, using getWave, to do the nonlinear time variant things that you might want to do, for example, an equalization in the receiver. And if you're running statistical, the waveform base, the getWave function is not used, but we use the impulse modification described on the previous slide in the AMI init. This is kind of modeling detail, but you as a simulator user should be aware that these things need to be dealt with and to look for them when you get a model. Sweeping parameters is supported inside of this flow, so that's another good thing. Clearly, if you're going to explore design space, you need to be able to see what happens if I change, for example, in this particular graphic, I can change the value of a tap. In this case, I think it was in pre-emphasis. And you can see, the top left-hand corner, that is like all of the different values mashed together. But you can go in and pull out, for example, the response at a particular tap value. So that's really all the detail I want to cover here in terms of the IBIS AMI and the channel simulation. Let's really get into this. And here at the end, this is kind of the easy part, if you like. We're going to see how this bolts together with an optical link. So what we do is we take that channel simulation and we break it in the middle, if you like, and add in the middle a section which is effectively our optical link. When we went back to talking about generating IBIS AMI models, we talked about the fact that you could produce a link that had, the laser driver, the VCSEL, the fiber, the detector, etc. Those things are all put inside of the AMI. So the optical link, including the fiber, is in a self-contained AMI model in the middle of the channel, if you like. So this allows us to do the electrical to electrical, which includes the optical fiber part of the system. If you look at it here, we think of the optical link as a redriver. That's kind of like a general term. So this could be electrical as well as optical at this particular position. The redriver model takes electrical in and gives out electrical. That keeps us in the electrical domain inside the channel simulation. All of the E to O and O to E stuff is done inside of that model. And this allows us to put this together with different SerDes models. Now, how do you get at things like fiber length or jitter parameters? Those become parameters that you can adjust on the optical link model itself. So that's an important part of the picture here, that even though the link is fully self-contained, you still have access to parameters related to that optical link from inside of the model, and therefore within the channel simulation environment. How does that work? Well, how does it look as a model? Well, actually, this is a little different from the earlier models in the sense that there are now actually two models contained in one IBIS file. One for what we'll call the receiving section, if you like, and one for the transmitting section of that mid-channel. Each model has its own, each half model, if you like, has its own AMI and DLL file associated with it. So that's good. And then basically they talk to each other in the context of the channel simulation. And you can cascade these together, so the idea being that if you define a mid-channel, you could use more than one mid-channel at a time. You could break this up into two if you wanted to. What does the IBIS file look like in this context? Well, it's very much like we described earlier, except now there are two models in one IBIS file. So when you're looking at a redriver construction, that's what you will see. This, again, sort of formalizes this in terms of what happens inside of the actual mid-channel IBIS AMI model. So you'll see that there is an IBIS section at the input and output, which go with the electrical simulation. And then internally, the first and second algorithmic sections are used to work across the optical link in the case of an optical link. And one thing to realize is that division is kind of arbitrary. One of them could be empty if you wanted it to be. So that tells you can balance the split between the receiving side and the transmitting side of mid-channel in any way that you choose. It's very flexible in that way. So this really then, when we get to the end of it all, this is what it could look like if you had a channel simulation set up with an optical link in the middle. So here you have a simple transmitter and receiver in the electrical section, a package model, if you like, a simple package model, and then inside of that, there's some kind of an optical link described with parameters like fiber length, gain, compression. Or anything that you really could parameterize with respect to the link can be exposed and therefore accessed here from the channel simulation. That really puts the optical link into channel simulation and shows that, yeah, we've got a great technique for analyzing a physical channel, and now we can include an optical link, and that then really supports the design for some of these very complicated high data rate systems that are coming down the line. So in conclusion, faster and faster data rates and new technologies mean that you really do have to simulate the full electric-optical link to understand it and to get the right characterization of it. A simulation environment for such a thing has to handle realistic bit error rate in the presence of DSP and high-fidelity analog distributed channel models. And you need to be able to interact with the simulation freely to explore the technology design space and understand the interaction, that trade-off between DSP and channel impairments. And that's really, you really need to be able to make those rapid, good quality design decisions. So those requirements, I hope I've shown, point towards channel simulation with its high-speed capability and its DSP analog modeling capability. And really, I think that is a really good choice for modeling the physical layer of an optical fiber communication system. So that's it for the presentation part. I guess we'll now move into the Q&A part of this talk.
Very good. So my name's Colin Royk. I'll be reading out the questions for Graham. I'm as Jessica mentioned, the product manager for High Speed Digital here at Agilent ESOF EDA. And the first question is the optical link redriver model available as a standard in ADS? And that's from Chad.
So the redriver model is available in the ADS channel simulator as of the ADS 2012.08 release. So yes, that redriver model is available. It's a standard part of ADS in the current product, yes.
I should add that it's part of the transient convolution element. It's not part of the ADS core. It's the whole transient channel simulator is in our transient convolution element, which is an add-on to ADS core. It's also in the bundles for high-speed digital. Next question is from On. Is the optical link simulation example available to us? I'm not sure, Graham, are these on the Knowledge Center or are they in the product? I can't remember how we ship these examples out.
The latest example, the one that I've been using, is one that I developed myself. It's a very basic, but it shows all of the parts. So if it's not on the Knowledge Center or in the product, I really can't give you a definitive answer on that right now. But if it isn't, feel free to drop me an email, or we'll take your email and I'll send that to you after this webcast.
Great. Maybe we can put that on the Knowledge Center and add it as on the follow-up email.
Okay, we can do that.
Next question is related to the vendors' usage of this technology. Are IBIS AMI models available from various vendors?
Oh, the answer to that is yes. Many IC vendors now are producing IBIS AMI models to describe their chip functionality in the SerDes world. So yeah, that's a definite yes. I see more and more companies doing that, and even to the extent now that some people are looking at producing IBIS AMI models of their optical modules as well. So it's one of those things that is very definitely being adopted. It's not universal yet, but I think it will be. I don't think there's any doubt about that.
And add to that, one opto vendor that's gone public, there are several that have adopted this methodology. One that's gone public on it is Avago. We published a joint paper with Avago DesignCon a year ago, and they're adopting this methodology. And there are several others that I'm not at liberty to name right now, but I think the answer is yes.
I think, the thing is, if you're interested in a particular chip or module from a vendor, ask them. And I think you'll be pleased with the answer.
Yeah, and if they don't have it, point them to this webcast, and we can get them generating the model very quickly with SystemVue. Yeah. So the next question from Lewis is, it's a very interesting question actually. Does bit-by-bit analysis provide more accuracy than statistical? That's a trick question for you there, Graham.
Yeah, no. So the answer is they're within the techniques, they're both accurate methodologies. The bit-by-bit and the statistical, for the same setup, given the restriction, the statistical has to have both linear time invariant channel and linear time invariance in the transmit and receive. If that is true for bit-by-bit and for statistical, yes, they should give the same answer. There shouldn't be one that's more accurate than the other. I guess statistical will give you a more accurate answer in the sense that you're running effectively an infinite number of bits. So you don't have to wait. And if you want like 10 to the minus 10 to the 15 bits or equivalent, or 10 to the 18, yes, the statistical will give you the better answer in that case.
Yep, bit-by-bit would require extrapolation in that case, Gaussian tail extrapolation, yep. So I think, the bit-by-bit mode gives you more flexibility, but if you have an LTI, as Graham mentioned, statistical is perfectly accurate, and you don't have to extrapolate the low PR contours. Next question also from Lewis. I see some folks using a bit pattern to generate the impulse response rather than a single pulse. Have you seen this, or do you do this in your tool? I can't think of a reason why you'd want to do that. Yeah, that's kind of hard.
I mean, so a true step response, or impulse response characterization contains everything that we need, I think, in order to do the kind of simulation that we do. I'm not aware of an advantage or a rationale to do it the other way. Clearly, if they're doing it, there must be a reason, but I'm not aware of it.
Yeah, I think mathematically, everything you know about a linear time invariant system is in that impulse response, so I can't think of a reason for that either. But maybe there is something we haven't thought of.
I'll just clarify. If your standard contains a specific bit pattern, then that's not necessary for characterization. But if you do need to use a specific bit pattern inside of a channel simulation, then you will, in that case, want to use the bit-by-bit mode, because the statistical methodology is for PRBS, so it's not specific bit pattern. Just want to add that.
It's a conceptually infinite bit pattern, yeah. Either AB, 10B, or uncoded, yeah. Several questions actually asking about part one of the seminar. I should explain that this series, all the 3 parts are standalone parts. It's not like you've missed anything by missing part one. The part one was actually on DDR4 was the topic, and it was a standalone, self-contained webcast, just as this one is. And part 3 is on jitter amplification. And I think we can send out the link to part 1, the on-demand recorded webcast of part 1, which, as I mentioned, was on DDR4 topic, with the follow-up email. And I think Carmine has just pushed out the invite to part 3. And again, it's a standalone webcast on a different topic, jitter amplification. So we'll send that link out to everybody who's asked for it. The question, let me press refresh here. I have to refresh the questions. So the question is, how could this technique be extended from rack to rack opto to long haul opto?
So that's an interesting question. I was actually reading around before doing this webcast that essentially the techniques that are currently used in long haul are things like wave division multiplexing and such like are being pushed back for their higher capacity and fidelity and things into these shorter links. It's really so. The net of this is I think the answer is yes. Certain parts of this will require simulators to be modified and adapted. But yeah, it's going to be a question of having models that represent the long haul accurately, and then measurements within the engine that support the kinds of formats that are used, the modulation, those kinds of things that are then used in the channel itself.
Yeah. So next question is from Chad. What palette is the IBIS AMI optical redriver model located? I think there may be some confusion there as to whether it's a separate component from the electrical redriver. So I think it's the same.
Yes, it's with the same as the other IBIS AMI model instances, and in ADS it's on the channel simulation palette. It's actually it's on the simulation palette itself, not in a separate library.
Yeah, channel sim. It has to be ADS 2012 or afterwards, and we use the same component for the electrical redriver as the optical redriver, and the only difference is you're loading an electrical to electrical model into that component using the .ibis file. So the symbols are identical to the electrical redriver. It's just that you're loading a different model, and internally the EO and OE processing is internal to the model. So as far as ADS is concerned, it's electrical in and electrical out. And the opto is kind of baked into the center of the model. Okay, I think that's all the questions covered, Graham. I think we can wrap up.
Okay, well, just again to the audience, thank you for attending. I appreciate you listening in to our webcast, and I think that's it for today.
Yeah. Jessica, do you have anything to add to wrap us up?
Yes, I do, and I'd like to thank both of you for joining us today, and I would like to thank everyone for attending today's webinar, Modeling Optical Fiber Communication with Channel Simulation, Part 2 of the Overcome High-Speed Digital Design Challenges webinar series, brought to you by Agilent and DesignCon Community. Please fill out and submit this survey at this time if you haven't done so already. By completing this survey, you'll provide Agilent and DesignCon Community with valuable feedback on the subjects covered in this webinar and how we can improve future broadcasts. This presentation will be available shortly in an on-demand format, and as a registered user, you'll receive an email with detailed information on how you can access the on-demand replay of the webinar. The on-demand will also include a PDF copy of the slides used in today's discussion. This webinar is copyright 2013 by DesignCon Community. The presentation materials are owned by or copyright by Agilent Technologies, which is solely responsible for their content. The individual speakers are solely responsible for their content and opinions. We hope you will join us for future webinars. For our current schedule of live and on-demand events, please visit us at designconcommunity.com. Thank you very much for joining us, and have a great day.